One of the issues that has come up with the description of electricity and magnetism and their corresponding forces has been the fact that the magnetic force depends on velocity. And the way this ends up working is that it actually ends up not being invariant from transformation of reference frames. So I wish to provide an example of what is happening there, why it doesn't make sense to us, and how special relativity fixes that. So for this example, we're going to have three different items. One, we have this long wire with positive charges, and those positive charges will be moving. There'll be some sort of current in this direction, so each positive charge will have velocity v. We'll also have a long wire of negative charge, and the two wires will have the same charge density other than a sign difference. Lastly, we'll have this positive charge moving along to the right, and it will also go with the same speed as the charges in the wire here. We've also set it up such that the distance between either of these wires and the charged particle are the same. It's kind of hard to draw that, so I need to explicitly state the distance between either wire and the charged particle is the same. So this means if we are looking in the frame that we call a rest frame, and in this case we say how about some charge on this wire here that we're saying is not moving. That's defining our reference frame. With that set up in our rest, or we often call the lab frame, we can first look at the electrical forces. So there'd be some sort of electric field from the lower wire, the negative wire, and we'd also expect an electric field from the upper wire, the positive one. And in fact, because these two are having the same charge density, the same linear charge density, they're supposed to be the same distance away. At the point of the charge here, both fields are of equal magnitude but of different signs, so they actually just add up to 0, which means that the electric force on that charge will just be 0. On the other hand, what about the magnetic field? Well, one of the things we should remember is that first the electric field from a long wire is equal to the linear charge density divided by 2 pi epsilon naught r, while the magnetic field, the B field from a long wire with a current traveling through, is mu naught I divided by 2 pi r. So in only one of these wires do we actually have any sort of current, only in the upper wire here. So this wire is producing a magnetic field, and the force from a magnetic field is supposed to be, at least in magnitude, QV times the B field, and in this case the velocity of our charged particle will be perpendicular to the B field created by the long wire here. So fortunately the cross product is nice and simple. It's just simple multiplication now. Nonetheless, then we have that force, and we can substitute what we have for B. So we'd have that the force on that charged particle is its charge, how fast it's moving, the amount of current in the wire, divided by 2 pi epsilon naught times the speed of light squared times r. You might have noticed that, of course, I'm using this expression here rather than mu naught. You're going to see why I want to do that later, but they are equivalent, since there is a nice straightforward relationship between the speed of light and the permittivity and permeability of space. This relationship right down here. So I just did a substitution. You'll see why I wanted to do that later. In the meantime, though, we have a problem if, instead of looking at the lab frame, what if we wanted to look at the situation from the point of view of this moving charged particle? If we're in its own frame, well, in its own frame it's not moving. And since the charges in the long wire here are moving along at the same rate as this charged particle in the reference frame of this particle here, these charges aren't moving. So according to this charged particle, there is no current in this wire. On the other hand, this wire is now moving backward with some velocity v. So there's a current in the point of view of this charge, so you'd say, all right, there's still a magnetic field. There's still some magnetic field, and it's ending up to being the same sort of magnetic field. Same magnitude, even. Problem is, though, in the particle's own reference frame, it's not moving. So if you were going to the same equation here, well, the velocity you'd be putting in there has to be 0. So there is no magnetic force at all on the charged particle. We still have the same electric fields from the two wires, so there's no electric force. So here's the big problem. In the lab frame, there is some force acting on the particle. In the particle's reference frame, classically, there's no force acting on the particle. This is obviously inconsistent. If we go from one reference frame to another and we can't agree that there's a force involved, we have a problem. And this is what special relativity will fix. So what will special relativity do for us? Well, one of the things I had mentioned was about the linear charge density of either wire, and I used the symbol lambda for that. Those charge densities are measured in the lab frame. Are they the same if we move to another reference frame? Actually, no. After all, because we are talking about linear charge density, well, our conception of length changes when we go from one reference frame to another. So how do we adjust for that? So for example, the linear charge density of the positively charged wire, how does that change? And what about the negatively charged wire? Well, in the negative case, it's fairly easy to guess. Well, that wire is going to actually appear to have been contracted. We would expect there to be some sort of length contraction because all those charges are now moving relative to the single charged particle moving along. So in that case, the distance between those charges will appear smaller because of length contraction. We'd expect the linear density to go up. So the original linear density we had divided by gamma, normal length contraction. On the other hand, the positive linear charge density for that one wire is actually, we're now going from the reference frame of the lab to the reference frame of the wire. All those charges were in the same reference frame as that single moving charge, so we're actually moving from not the proper frame to the proper frame for measuring linear charge density in that wire with moving charges. So in fact, it's going to actually have the sort of opposite effect. It's going to be gamma times the original linear charge density. So this means that basically the negatively charged wire is going to appear to be more densely packed with negative charges, and the positively charged wire is going to appear to be less packed in with positive charges, all because of our transformation of reference frame. So we do have these two wires. We could basically combine the two effects in our new reference frame, the reference frame now of the particle moving along. So if we look at that sort of total, it's basically just going to be the addition of the two linear charge densities in our new frame. And we can rewrite that as simply lambda. We'll have the same magnitude from our original form, then multiplied by gamma minus 1 over gamma. So we're substituting in the minus sign here because of the fact that this linear charge density is negative, dividing by gamma because of what we have here, multiplying by gamma because of what we have here, so simple substitution there. Now, this factor of gamma minus 1 over gamma, we also know that gamma is equal to 1 over square root of 1 minus v squared over c squared. if you do a fair amount of algebra, and I'm not going to repeat it here to show the result, you can demonstrate that this actually simplifies out fairly nicely, and the result you're going to get overall when you plug that result in is you're going to get negative lambda v squared over c squared. Again, I leave the algebra as an exercise to the reader. So now we see there's actually going to be some sort of net linear charge density now that we've moved from the lab frame to the particle frame. So we will take that result, and let's also put in one more key point about our definition of current that we have. Well, current is supposed to be just basically the movement of charges, how fast charge is moving along, so we can substitute. That is simply then going to be how much charge we actually have divided by how quickly it's moving, the time involved. So charge is moving at the time. Well, we can actually do a bit of substitution since we also know that velocity is just distance over time. And since we have also knowing that linear charge density is just how much charge you have per unit length, the units would work out such that we can replace this as linear charge density times velocity. That this would be an equivalent statement. So if we do that, and we now go to our equation of electric force, we know that is supposed to be Q times the strength of an electric field, and as we stated before, the electric field now is going to actually exist because we now have some net linear charge density from our wires moving to the new reference frame. And using the result of what is supposed to be the electric field from a wire, we can plug that in, and we're going to find that the force is negative Q linear charge density, and this is the charge density of either wire originally in the lab frame. Speed of our particle squared divided by 2 pi epsilon naught c squared times r. So far so good, and I can substitute in our definition for current as I have up here. And if I do that, I'm going to get negative QVI divided by 2 pi epsilon naught c squared r. That should look familiar. This is the exact same form we had for the strength of the force from the magnetic field. Same in magnitude. We see that there's a minus sign here, but if you're careful and you go back, and you'll see that in either case, the force ends up being in the same direction. That would have been more apparent if I had properly put through all the information of the cross product and set up a coordinate system, but it's the same magnitude, and it's also in the same direction. In both cases, the force is towards our wires. So this is the sort of general result we have. We can now actually make sure that in both reference frames, when we switch from the lab frame to the particle frame, or any other frame if we so choose to show that, we will still get the same magnitude and direction of force. We've now actually restored our invariance of reference frames. However, what has changed from one case to another is, in the lab frame, we said the force was due to a magnetic field, that it was a magnetic force. In our new reference frame, the force is due to an electric field. It's an electric force. And in other frames, we're actually going to find it's some combination of the two. The invariance, then, is that what we call the electric and magnetic field is due to your point of view. So this is the fantastic result. What you call an electric or magnetic field depends on how you are moving relative to the charges. So this is the fascinating sort of thing that makes sense ultimately of electromagnetism. The electric and magnetic fields are really the same thing. It just depends on how you're moving relative to their sources. And in general, we could show that, but I'm not going to, but that was what really made Einstein's theory so amazing. Not only all the other facts of how it bends our notions of space and time, but also it can make electromagnetism consistent across all reference frames.